All right, where do we leave off on here? Library functions. No, syscalls for getting users and group information. So man to get pwnam. Let's see. No, standard library. Not a syscall. Okay. Let's just start at the top page. Because they return a pointer to a statically allocated memory, get pwnam and get pwuid are not reentrant. Not reentrant means that you can't call them multiple times. Can't call them from themselves. Reentrant in Java, or at least with locks, mutexes in Java, is where you acquire the lock in a specific thread, and then you can acquire the lock again from the same thread. It just doesn't allow any other threads to acquire the lock. It's reentrant for locking. But what does he mean here? Because they return a pointer to statically allocated memory, get pwnam and get pwuid are not reentrant. In fact, the situation is even more complex, since the return password structure contains pointers to other information, e.g. the pw name field, that is also statically allocated. We explain reentrancy in section 21.1.2. Similar statements apply to the get group name, get group ID functions described shortly. So he's making a reference to 21.1.2. Let's pull that up real quick. Go to 21.1.2. Reentrant and async signal safe functions. Reentrant and non-reentrant functions. To explain what a reentrant function is, we need to first distinguish between single-threaded and multi-threaded programs. Classic Unix programs have a single thread of execution. The CPU process instructions for a single logical flow of execution through the program. In a multi-threaded program, there are multiple independent concurrent logical flows of execution within the same process. In chapter 29, we'll see how to explicitly create programs that contain multiple threads of execution. However, the concept of multiple threads of execution is also relevant for programs that employ signal handlers. Because a signal handler may asynchronously interrupt the execution of a program at any time, the main program and the signal handler in effect form two independent, although they're not concurrent. They're concurrent, but they're not parallel, I would say. Two independent, although not concurrent threads of execution within the same process. The function is said to be reentrant if it can be safely, so that means you can't call it from the signal handler. Executed by multiple threads of execution in the same process. In this context, safe means that the function achieves expected results regardless of the state of the execution of the thread of execution. That's not my understanding of reentrancy from Java. in POSIX, Unix, explain concept of reentrant functions. Did you spell that? Yeah, reentrant. A reentrant function is a function that can be safely called again, re-entered, before its previous execution is complete, without causing any undefined behavior or data corruption. It's a different meaning than a reentrant lock. This can happen if the function is called from multiple threads concurrently. The function is called from a signal handler while it was already running in the main program. Key properties of reentrant functions. For a function to be reentrant, it must not rely on shared state that can change unexpectedly. Specifically, a reentrant function does not use static or global non-const data. Example, non-reentrant. Okay. Does not return pointers to static data unless that data is protected by locks or local to the thread. Shared static memory can break reentrancy. So you have global memory being returned. Want to call this other reentrant functions directly or indirectly. I mean, reads, you can do concurrent reads all you want. It's if you do writes. Let's just use here as example, get pw name is non-reentrant because it returns a pointer to statically allocated memory. Why is this? Explain why this is an issue for this library, standard library function. It returns a pointer to a struct password containing user info. Why it's not reentrant? The standard function typically uses a statically allocated inside the library to store results. That means struct password overwrites this. Oh, so we're writing the same. Oh, I see. It's a mutable static variable that's being mutated every time you call it. Yeah, that's not good. But that's the mutation. So it's not the reading, it's the mutating. That's the issue. Yeah, they have the reentrant versions. So this one, get pw name, is just a name, but now we have to pass in size t, the struct password, a character buffer restricted by the size, another size t. Oh no, these are different alternatives, right? No. This is the alternative. So you can call it with just a size t. I hate reading these signatures. Const char name, and then you give it the struct that you want it to write into, and then you give it a character buffer with a restriction size, passing size, and then give it a pointer to point. Oh, this is for the result. I don't know how to call that. Anyways, I don't really care. Let's continue on. SusV3 specifies an equivalent set of reentrant functions. Get PW name R, so-and-so, so-and-so, that include as arguments both a password or group structure as a buffer area to hold the other structures to which the fields of the password group structure point. The number of bytes required for this additional buffer can be obtained using the call sysconf get pwr size max, so-and-so. In the case of the group related functions, see the manual pages for details of these functions. According to SusV3, if a matching password record can't be found, then get pwnam and so-and-so should return null and leave error note unchanged. This means that we should be able to distinguish the error and the not found cases using code such as the following: struct password, error note, get pw name. Yeah. However, a number of Unix implementations don't conform to SusV3 on this point. If a matching password record is not found, then these functions return null and set error node to non-zero values such as ENO, ENT, or ES or C. Before version 2.7 glibc produced the error ENO, ENT for this case, but since version 2.7 glibc conforms to the SusV3 requirements, this variation across implementations arises in part because POSIX 1990 did not require these functions to set error no on error and allowed them to set error no for the not found case. The upshot of all this is that it isn't really possible to portably distinguish the error and not found cases when using these functions. Retrieving records from the group file. The so-and-so functions retrieve records from the root file. Whoop. The get group name function looks up group information by group name, and the get group by D function performs a lookup by group ID. Both functions return a pointer to a structure of the following type. The gr password field of the group structure is not specified in SusV3, but is available on most Unix implementations. As with the corresponding password functions described above, the structure is overwritten on each call to one of these functions. If these functions can't find a matching group record, then they show the same variation in behavior that we described for get pwnam and get pwuid. Example program. One common use of the functions that we already described. The section is to convert the symbolic user and group names to numeric IDs and vice versa. Lesson 8.1 demonstrates these conversions in the form of 4 functions, blah blah blah, and the convenience to the caller. Also allow the name argument to be purely numeric string. In that case, the string is converted directly to a number and returned to the caller. We employ these functions in some examples later in the book. I don't really care. They're just convenience functions. Scanning all records in the password and group files to set PW entries. Sequential scans of the records in the password file. The get PW entry function returns records in the password file. 1.1, returning null when there are no more records or an error occurs on the first call. So-and-so automatically opens the password file. Then when we have finished with the file, we call end pwent to close it. We can walk through the entire password file, printing login names and user IDs with the following code. Don't care about that. The end so-and-so call is necessary. Huh? It's necessary so that any subsequent get PW entry calls, perhaps some other part of the program or some library function that we call, will reopen the password file and start from the beginning. On the other hand, if we are part of the way through the file, we can use set pwnt function to restart from the beginning. The functions perform analogous tasks for the group file. We omit the prototypes for these functions because they are similar to those of the password file functions described above. See the manual pages for details. Retrieving records from the shadow password file. The following functions are used to retrieve individual records from the shadow password file and to scan all records in a file. Not interesting. We won't describe these functions in detail, thank you. Since their operation is similar to the corresponding password file functions, these functions aren't specified in SUSV3 and aren't present in all Unix implementations. The get sp name and get spent functions return pointers to a structure of types spwd. The structure has a form of so-and-so. Amazing. We demonstrate the use of get spnam in listing A2. Password encryption and user authentication. Some applications require user authentication themselves. Authentication typically takes the form of username, login name, and password. An application may maintain its own database of username and passwords for this purpose. Sometimes, however, it is necessary or convenient to allow users to enter their standard username and password as defined in etc password, etc shadow. For the remainder of this section, we assume the system where password shadowing is enabled, and thus that the encrypted passwords are stored in etc shadow. Network applications that provide some form of login to a remote system, such as SSH, FTP, are typical examples of such programs. These applications must validate a username and password in the same way that a standard login program does. For security reasons, Unix systems encrypt passwords using a one-way encryption algorithm, which means there are no methods for recreating the original password from this encrypted form. Therefore, the only way to validate a candidate password is to encrypt it using the same method and see if the result matches the value stored in etc shadow. The encrypted algorithm is encapsulated in the crypt function. So you call crypt, gives you back a char star, you give it a key char star, which is the password, and a salt. And this is part of the xopen stuff. Returns pointer to statically allocated string containing encrypted password on success or null on error. The crypt algorithm takes a key. Is there a crypt R? That's reentrant. Man crypt. Yeah, it's a crypt R. The crypt algorithm takes a key, a password of up to 8 characters and applies a variant of the data encryption standard algorithm to it. The salt argument is a 2-character string whose value is used to perturb vary the algorithm, a technique designed to make it more difficult to crack the encrypted password. The function returns a pointer to a statically allocated 13-character string that is the encrypted password. Details of DES can be found at so-and-so. As noted earlier, other algorithms may be used instead of DES. For example, MD5 yields a 34-character string starting with a $, which allows crypt to distinguish DES encrypted passwords from MD5 encrypted passwords. In our discussion of password encryption, we use the word encryption somewhat loosely. Accurately, DES uses the given password string as an encryption key to encode a fixed bit string, while MD5 is a complex type of hashing function. The result in both cases is the same, an undecipherable and irreversible transformation of the input password. Let's run that man page again. Let's see if Shaw is listed anywhere. No. Oh, I'm on the wrong page here. Yeah, there we are. Both the salt argument and the encrypted password are composed of characters selected from the 64 character set. Thus, the 2-character salt argument can cause the encryption algorithm to vary in any of 4096 different ways. This means that instead of pre-encrypting an entire dictionary and checking encrypted password against all words in dictionary, a cracker would need to check the password against 4096 encrypted versions of the dictionary, which isn't too big. The encrypted password returned by crypt contains a copy of the original salt value as its first 2 characters. This means that when encrypting a candidate password, we can obtain the appropriate salt value from the encrypted password. Wait a minute. The encrypted password returned by crypt contains a copy of the original salt value as its first 2 characters. This means that when encrypting a candidate password, we can obtain the appropriate salt value from the encrypted value. That's typical. Encrypted password value already stored in Etsy Shadow. Programs such as password1 generate a random salt value when encrypting a new password. In fact, the crypt function ignores any characters in the salt string beyond the first 2. Therefore, we can specify the encrypted password itself as a salt argument. That's not really good, because that means that the attacker can just read the salt and know the first 2 characters of the password for brute forcing. So, not sure that's a good idea. In order to use crypt in Linux, we must compile programs with the lcrypt option so that they are linked against the crypto library. Listing 8.2 demonstrates how to use crypt to authenticate a user. This program first reads a username and then retrieves the corresponding password record, and if it exists, shadow password record. The program prints an error message and exits if no password is found, or if the program doesn't have permission to read from the shadow password file. This requires either super user privilege or membership of the shadow group. The program then reads the user's password using the getPass function. The getPass function first disables echoing and all processing of terminal special characters such as the interrupt character, normally Control C. We explained how to change these terminal settings in chapter 62. It's way at the end of the book. It then prints the string pointed to by prompt and reads the line of input, returning the null terminated input string with the trailing new line stripped as its function result. This string is statically allocated and so will be overwritten on subsequent calls to getPass. Before returning getPass restores the terminal settings to their original states. Having read a password with getPass, the program listening it to them validates that password using the crypt to encrypt it and checking that the resulting string matches the encrypted password recorded in the shadow password file. If the password matches, then the ID of the user is displayed, as in the following example. So we get into root, and then we say check password on MTK. Successfully authenticated. Okay. The program listening 8.2 sizes the character array holding a username using the value returned by which yields the maximum size of a username on the host system. We explained the use of sysconf in section 11.2. I don't really care about this program. I'm sure it's great. Let's think 8.2 illustrates an important security point. Programs that read a password should immediately encrypt that password and erase the unencrypted versions from memory. This minimizes the possibility of a program crash producing a core dump file that could be read and to discover the password. There are other possible ways in which the unencrypted password could be exposed. For example, the password could be read from the swap file by a privileged program if the virtual memory page containing the password is swapped out. Alternatively, a process with sufficient privilege could read devmem, a virtual device that presents the physical memory of a computer as a sequential stream of bytes. Yeah, that would allow them access. I didn't know about devmem. In an attempt to discover the password, the getPass function appeared in SUSV2, which marked it legacy, noting that the name was misleading and the function provided functionality that was in any case easy to implement. The specification of getPass was removed in SUSV3. It nevertheless appears in most Unix implementations. Summary: each user has a unique login name and an associated numeric ID. Users can belong to one or more groups, each of which also has a unique name and an associated numeric identifier. The primary purpose of these identifiers is to establish ownership of various system resources, files mainly, and permissions for accessing them. A username and ID are defined in the etc password file, which also contains other information about the user. A user's group membership are defined by fields in the etc password and etc group files. A further file, etc shadow, which can be read only by privileged processes, is used to separate the sensitive password information from the publicly available user information in etc password. Various library functions are provided for retrieving information from each of these files. The crypt function encrypts a password in the same manner as a standard login program, which is useful for programs that need to authenticate users. Exercises: when we execute the following code, which attempts to display the usernames for two different user IDs, we find that it displays the same username twice. Why is it? Because it's not reentrant. Implement get PW name using, I'm okay on that. I'm not going to do that last one, but I'll just check the answer on solutions here. 8.1. Yeah. Yep. It's not reentrant. Cool. That is that chapter. And if I L/LA chapter 8, I don't think I had anything in there. Oh, yeah. Chapter 8 was just like kind of boring. Then readme. I guess because I didn't really learn anything. That's why it was kind of boring. Bunch of library functions that if you ever need them, you could just look them up. Process credentials. I did learn about the G shadow file. I wasn't familiar with that. Git status, git DC, git CI. We'll say finish read chapter 8. Get LGA. Yep. Yeah. 7:30 now. Yeah, might as well make some more progress on this. Let's see. Check chat. Nope. Okay. Every process has a set of associated numeric user identifiers, UIDs, and group identifiers, GIDs. Sometimes these are referred to as the process credentials. These identifiers are as follows: the real user ID and group ID, effective user ID and group ID, saved set user ID and saved set group ID, file system user ID and group ID, Linux specific, and supplementary group IDs. In this chapter, we look at this. This is going to be a lot of stuff that I don't know. I only know a little bit of. But in this chapter, we look in detail at the purpose of these process identifiers and describe the system calls and library functions that can be used to retrieve and change them. We also discuss the notion of privileged and unprivileged processes and the use of the set user ID and set group ID mechanisms, which allow the creation of programs that run with the privileges of a specified user group. Real user ID and real group ID. The real user ID and real group ID identify the user and group to which the process belongs. As part of the login process, a login shell sets its real user and group IDs from the third and fourth fields of the user's password record in the etc password file. Boom. When a new process is created, usually when a shell executes a program, it inherits these identifiers from its parent. Effective user ID and effective group ID. On most Unix implementations, Linux is a little different, as explained in section 9.5. The effective user ID and group ID, in conjunction with the supplementary group IDs, are used to determine the permissions granted to a process when it tries to perform various operations, e.g. system calls. For example, these identifiers determine the permissions granted to a process when it accesses resources such as files and system v interprocess communication IPC objects, which themselves have associated user and group IDs, determining to whom they belong. As we'll see in section 20.5, the effective user ID is also used by the kernel to determine whether one process can send a signal to another. Okay. A process whose effective user ID is 0, the user ID of root, has all of the privileges of the superuser. Such a process is referred to as a privileged process. Certain system calls can be executed only by privileged processes. In chapter 39, we describe Linux's implementation of capabilities, a scheme that divides the privileges granted to the superuser into a number of distinct units that can be independently enabled and disabled. Normally, the effective user and group IDs have the same values as the corresponding real IDs, but there are two ways in which the effective IDs can assume different values. One way is through the use of system calls that we discuss in section 9.7. The second way is through the execution of set user ID and set group ID programs. Set user ID and set group ID programs. A set user ID program allows a process to gain privileges it would not normally have by setting the process effective user ID to the same value as the user ID owner of the executable file. A set group ID program performs the analogous task for the process's effective group ID. The terms set user ID program and set group ID program are sometimes abbreviated as set UID program and set GID program. Like any other file, an executable program file has associated user ID and group ID that defines its ownership of the file. In addition, an executable file has two special permission bits, the set user ID and set group ID bits. In fact, every file has these two permission bits, but it is their use with executable files that interests us here. These permission bits are set using the chmod command. An unprivileged user can set these bits for files that they own. A privileged user, cap F owner, can set these bits for any file. Here's an example. I'm going to su into root, and then ls-l on program, and it has regular file, read write executable on owner, read and executable on group, and read and executable on all. And then you change mod u plus s, turn on the set user permission bit, and group plus s. So plus s is just set. Got it. So if I have a file, I'm just gonna go and vim up or mkdir under temp ASDF. Yeah, we just go under here and say I echo some garbage into a foo file. Here I have change mod plus x on the foo. And then if I do change mod plus minus x on foo, what if I do plus xs? No. Let's do x. Sorry, plus xs. That's what I meant to do. So the execution bit then has s set on those two, but say I want to subtract just the user set bit and just leave the group. Did I do that correctly? Sorry, I need to do minus. Yeah. No. Yeah, that worked because it turned the S into an X here. All right, I just wanted to play around with that. Get some. Actually, you know what? Yeah, let's do that. CD or jump to chapter. Let's go there. mkdir chapter 9. And here I want to vim up we'll say user or creds.c main, and I'm gonna just go to AI and be like, write me a super simple program that lists out the process's credentials, effective and real user slash group, and what are the other credentials? Group IDs. Yeah, just give me the thing. Gimme. Okay, copy code. It says error no is not needed. We'll just say exit success. This will be exit failure. Exit failure, bam. So we get UID, get effective UID, get GID, get effective GID, and then real is real and effective basically. And then here we just print out the UID, GIDs, and then we call get groups. It gives back the number of groups. If it's less than 0, there's an error. We didn't really check any of these that they could error out. They can throw. Okay, well that's not good. Let's check the man page on these. Man up 3 for get UID. Is there a man 2 for that? Yeah, cool. Get UID and get EUID. Are these the system calls? Where are we located? Unix standard. Man get UID from 3. UIDT void 2. Same thing. Man syscalls. Man syscalls. Get UID. Yeah. These are syscalls. Get EUID. Yeah. So how do I know if these are calling the syscall variants and not something else? So I go to definition, it goes here to the Unix standard. I guess it doesn't matter, right? Alright, let's delete this error, no H. Alright, then we say, I'm gonna, what? Get groups, this gives you back the number of groups, and then I allocate the space for the groups, and then I have to call get groups again to get the actual groups, and then I can print out supplemental groups. Okay. Let's copy over some things here. rsync avz ci from chapter 7 into chapter 9 / cd into chapter 9. We're rm rf or rm free star. We don't want any of that. rm-r build. rm-r ref malloc. Mem malloc. Yeah. Anything else in here? That's all library stuff. Creds make. Oh, the .clang d needs to get updated. Chapter 9. I do make here. Alright, and then I do build creds. It's like, hey, yeah, cd and build. I want to say su do-i. And then here I want to say cd into C0 source, GitHub, TLPI, chapter 9 build. And then on creds, what I'm going to do is say, okay, you're going to get my group ID. So we say, I'll have to change own C0 root on creds. So now it's in the root group. And then if I change mod group plus S on creds, sorry. Now I got the set bit there. And now I can come out of here and rerun creds, and its effective group is root. Is there a root group? There is not a root group. If I cat out etc groups, let me, I don't know if I'm using the shadow thing for my groups file, so I'm just gonna blur. All right, so there is a root group. basically but now if I RM, can I RM? If I can make clean, yeah, it works. Cool. All right. Where are we? We just set permissions on that stuff. All right, as shown in this example, it is possible for a program to have both of these bits set, although it is uncommon. Yeah. When ls-l is used to list the permissions for a program that has a set user ID or set group ID permission bit set, then the X that is normally used to indicate that the execution permission is set is replaced by an S. When a set user ID program is run, loaded into a process memory by an exec, the kernel sets the effective user ID of the process to be the same as the user ID of the executable file. Running a set group ID program has an analogous effect for the effective group ID of the process. Changing the effective user or group ID is, in this way, gives a process, in other words, the user executing the program, privileges it would not normally have. For example, if an executable is owned by root superuser and has a set user ID permission enabled, then the process gains superuser privileges when that program is run. Set user ID and set group ID programs can also be designed to change the effective IDs of a process to something other than root. For example, to provide access to a protected file or other system resources, it may suffice to create a special purpose user group ID that has the privileges required to access the file, and create a set user ID, set group ID program that changes the effective user group ID of a process to that ID. This permits the program to access the file without allowing it all the privileges of the superuser. Sometimes we'll use the term set user ID root to distinguish a set user ID program that is owned by root from one owned by another user, which merely gives the process the privileges according to that user. We have now started using the term privilege in two different senses. One is the sense defined earlier, a process with an effective user ID of 0, which has all of the privileges according to root. However, when we are talking about a set user ID program owned by a user other than root, we'll sometimes refer to a process as gaining the privileges according to the user ID and of the set user ID program, which sense of the term privileged we mean in each case should be clear from the context. For reasons that we'll explain in section 38.3, the set user ID and set group ID permission bits do not have any effect for shell scripts on Linux. I gotta just hear what they have to say on that. 38.3. You gotta look that up. You can't just leave me hanging on that. 38.3. Be careful when executing a program. Caution is required when a privileged program executes under another program, either directly via an exec or indirectly via system POP or system library function. Drop privileges permanently before executing another program. If a set user ID or set group ID program executes another program, then it should ensure that all process. Oh, and shells are just like rampantly running other programs. Then it should ensure that all process user group IDs are reset to the same values of the real user group ID so that the program doesn't start with privileges that also can't require them. One way to do this is to reset all of the IDs before performing the exec using a technique described in section 38.2. Same result can be achieved by preceding the exec blah blah blah. I want to just hear what they have to say about shell programs. Here it is. Avoid executing a shell or other interpreter with privileges. Privileged programs running under user control should never exec a shell either directly or indirectly via system, popen, exec lp, exec vp, or other similar library functions. The complexity and power of shells and other unconstrained interpreters such as awk mean that it's virtually impossible to eliminate all security loopholes even if the exact shell doesn't allow interactive access. The consequent risk is that the user may be able to execute arbitrary shell commands under the effective user ID of the process. If a shell must be execed, ensure that privileges are permanently dropped beforehand. An example of the kind of security loophole that can occur when executing a shell is noted in discussion of system in section 27.6. A few Unix implementations honor the set user ID and set group ID permission bits when they are applied to interpreter scripts, so that when the script is run, the process executing the script assumes the identity of some other privileged user. Because of the security risks just described, Linux, like some other Unix implementations, silently ignores the set user ID and set group ID permissions when executing a script. Even on implementations where set user ID and set group ID scripts are permitted, they should be avoided. Interesting. Basically, they're saying scripts are insecure. But that's like every interpreted language then. Anything other than a binary, it's like, nope, you can't use these set user ID and set group ID bits. And to demonstrate that, I'm going to just ask AI here. Let's just actually go back to this. Write this same program but in Bash. Copy code, vim creds.sh, and if we do l/la, get status, get etl, get status. I want to try, I don't think get tracks these bits, but if I change mod plus x, the creds.sh, Git's gonna recognize that. Creds.sh, bam. Effective user ID. Shouldn't this be GID? That isn't exactly correct. It's trying to output a effective group ID, but uses EUID, which is the user ID. Okay, this looks a little bit more sensible. Okay, step out of creds. Yeah. And if I change sudo -i okay, cd, or can I just jump to chapter 9 here? No. C0 source, sorry, C0 source GitHub, yeah, TL chapter 9, and then here I have 2 terminals because I don't want to keep on bouncing back and forth. Jump to chapter 9, and then here we're going to say change mod to C0 root on creds.sh. Sorry, change own, not change mod. Set techo vi. And then change lshla. So that looks right. And then we'll say change, or do a git status here, it's not going to complain about that. But if I do a change mod group plus s creds.sh, so it's got the bit set. Git doesn't care. All it tracks is an execution bit. Does it track 3 separate execution bits? Like if I remove man change mod, there's the flags a. Okay, so change mod a minus x for creds.sh. Oh, that's all. Okay, that's not what I wanted. Okay, change lshla g. No, lowercase g. Lag. Okay. Change mod user and owner plus x. Sorry, user is owner group on creds.sh. Okay, git status. Yeah. Git doesn't track individual execution bits. It's like 1 bit for the whole thing. Git status. All right. Now we got to rerun this thing. It gives us the group. All right, and now when I run creds.sh, it's effective group ID. It's still 1,000. And if I do the same thing for user, and I change own of roots of creds.sh. All right, and now I can't even run it. Permission denied. So I have to say change mod plus x on creds.sh. And now I can run it, but I still don't get any of those permissions. Yeah. Then creds.sh. Say this program demonstrates that shell scripts on Linux do not have their effective user group set from set u gid bits. To demonstrate this, we'll have to set these bits on this script since these bits along with user owner group on the file to, I'll just leave it at that. Can I do a GQ? No. But I can go to line 80 here, or column 80. It's about here. So I'll break here. Boom. Oops. Why does it do that? So annoying. Okay, good enough. Oops. Read only operation. Yes. Cat creds.sh. I gotta change the owner on this thing. Change owner back to Why don't we just say change mod 666 to creds.sh. There we go. 777, sorry. There we go. Okay. Fine. Great. Kill this. Okay, I'm going to highlight that. Examples of commonly used set user ID programs on Linux include password, which changes the user password, mount and umount, which mount and unmount file systems, and su, which allows the user to run a shell under a different user ID. For example, an example of a set group ID program is wall, which writes a message to all terminals owned by the TTY group. Normally every terminal is owned by this group. I've never used wall, I don't think. Man, nope. I'll go back. Here, maybe? Good enough. Let's run. I'm gonna kill this one and this one. Clear man wall. 1, yeah. So can I do like a bunch of terminals and say wall, hello world? No, echo into wall. No. Man wall. Let's try like maybe sudo -i. Why is wall not working? Well, I wrote it to the sudo, but all my terminals it didn't. If I do another sudo over here, see. Yep. So it doesn't include my terminals. I do command, let's go over to AI. I want to use wall to write a message to all of my terminals, but instead it sends it to all other users' terminals, but not mine. Just tee it into your own TTY, yeah. Can I do that? T dev TTY into wall. Hello world. And then I say, how are you today? And I hit Control D, then broadcast everything. It's not exactly the same. Alright, enough of this. Alright. In sections 8.5, we noted that the program in listing A2 needed to be run from a root login so that it could access the Etsy shadow file. We could make this program runnable by any user by making a set user ID root program as follows. Make this program owned by root with a set user ID been enabled. Let's see here. We're at 9.4. We got lots more to read. It's 8:05. Yeah, this is just a short session here to get through. Really, I wanted to get through the last of chapter 8 before the end of the evening. And I'll just read down to here. So this just runs check password now as end user. The set user ID, set group ID technique is useful and powerful tool, but one that can result in serious in security breaches and applications that are poorly designed. In chapter 38, we list a set of good practices that should be observed when writing set user ID and set group ID programs. This is an unprivileged login. Who am I? MTK, but we can now access the shadow password for using this program. Cool. Cool. Alright, I'm going to leave off here at 9.4. Let me do a get status on this, get at all, get DC. That looks good. That looks good. These are my test programs. That's a bunch of ref stuff. Okay, get status. I'm going to blow away RMR ref for now. Make clean, get status, get at all, get status. Because that's all I really need. Get CI, we'll say progress on chapter 9. Push that. And we'll resume from here tomorrow. Cool. And then I'll just go down here. I don't need to. There's a lot of exercises here. That's good. Only one C file. I'm going to close that and just reload here. Alright, and then if I do my task warrior, I could say T7 and 8 done. Done. Okay. So now I'm 12% complete with reading it. Approximately. Cool. Alright, that's it for tonight. I'll be on tomorrow morning.